I really wanted it to be a Blackboard talk, but then because in my last 2 tutorials I was short of time, so I just wrote down a few things. It's not a presentation, it's just the things that I want to cover, but I want to save time writing on the board. So I'll be going a little in a way that you can follow with this. All right, so this is supposed to be a lecture in GA as well as in GAP, I mean the group algebra and GAP. So what I'll do is I'll relate to one of the topics that we had. Okay, so in Professor Eric Jesper's lecture, we have seen, we wanted to really understand this group ring, and we have seen with various examples that one of the ways to handle this, or one of the tools to handle this, is Wedderburn decomposition of group algebra QG, right? And finding Wedderburn decomposition of rational group algebra or any semi-simple group algebra is important in its own light also. This is one of its application. So I'll explain a method which is due to, which is with respect to computing Shoda pairs and then finding out the Wedderburn decomposition for a group G, for a group algebra. Okay, so what is first good thing about this method is, if you are talking of rational group algebra, you just play with the group G, the subgroup structure of the group G, right? That is something good about it. Motivation comes from, as has been mentioned earlier in the lecture, it comes from Shoda's irreducibility criteria, which tells you when a linear character is induced to the group G, a linear character of a subgroup G, subgroup of G is induced to G, when is it irreducible? That criteria is rephrased in terms of Shoda pairs, okay? This criteria you have already seen, I've just listed it for recalling. So you have a pair of subgroups which satisfy certain conditions, okay? And so how do you relate the two? If you have a Shoda pair, H comma K, H is a group whose linear character you take and which has kernel K, then if you induce it to G, the character that you get is going to be irreducible if and only if this is Shoda pair, okay? All right, then we have also seen that primitive central idempotent is associated to this, and this is a group ring element. There's alpha associated to it, a rational number alpha, so it's a multiple of EGHK, which is an idempotent. And we saw that the ideal case for us will be, or for some reason an easy case, a particular case will be when alpha equals to 1. We also check that this occurs if the primitive central, if the idempotents epsilon HK, which appear here, they happen to be orthogonal, right? This is just recalling the facts that we have already seen. So in case that happens, our work becomes a little easier, all right? And that is called as, so that motivates the definition of strong Shoda pair. So what we do is, what is known about strong Shoda pairs. Okay, so just a brief remark. If you look at the trivial character of G, it's character of G, so the associated Shoda pair is G comma G. Everything goes to the kernel, right? So what is the idempotent that you're getting corresponding to it? That is simply G hat, and we have checked that it is indeed an idempotent. All right, so the definition of strong Shoda pair, motivated by the fact that we want alpha equals to 1, and then there's another reason to it that we see along the lecture. So this is how strong Shoda pair is defined. If you have K normal in H, which is normal in the normalizer of K in G, and then there's another condition that H mod K is cyclic, which was needed for Shoda pair also, and it is maximal abelian subgroup of the quotient group normalizer by K. Along with that, we want G conjugates of epsilon HK to be orthogonal. And this indeed is a Shoda pair, though we do not see the condition that we had in Shoda pair, but this has been checked that it is indeed a Shoda pair. Okay. So what is good thing about strong Shoda pair? Of course, we are putting some conditions, so maybe we are losing out few things, but then what is good thing about strong Shoda pair is that the simple component corresponding to the primitive central idempotent obtained by a strong Shoda pair is known. Okay. In fact, to update this corresponding to a Shoda pair also, what is the component has been recently studied. I have not included it here, and in case you want to know more about it, you can discuss with Professor Bakshi or Kaur. Okay, so that's recent work, but I'm not including it here for the time being. All right, so the motivation behind strong Shoda pair was to see the simple component associated to it, and that's how, and this is a simple component. This already we have. Okay. So this is the simple component, and has been pointed earlier also that it does not really look very nice kind of structure, but then it is good. How it is good, or like what are the good things about it, we will see through some exercises maybe. So it may not be good for all the groups, but at least for some good classes of groups, it gives us very nice answers. All right, and just few remarks about it. The action that we have here is always faithful. You begin with a pair H comma K, which is strong Shoda pair, then the action which is coming in the cross product, that's always faithful. And in case twisting is trivial, that makes our work easier, right? So that brings it down to a matrix algebra over a field. All right, and then we wanted to make it even easier, because checking orthogonality of this epsilon hk, that also in itself is work. All right. So if we put additional condition that the group H in the pair hk is normal, the condition of orthogonality is automatically satisfied. I mean, if you just impose this condition that H also should be normal in G, with these two conditions, this happens to be a strong Shoda pair. Okay? So just we have a Shoda pair, we put additional condition that epsilon hk, those are orthogonal, we get strong Shoda pair. We put one more condition that H is normal in G, we get extremely strong Shoda pair. Okay? I hope I'm not confusing all the concepts. We'll come to these again. Sorry. Okay, so these are simple group theoretic conditions which one can check for any pair, right? You have a group, you can find out its subgroups in case you can, then you just need to check these two conditions and you know if it is extremely strong Shoda pair or not. All right? And because it is a strong Shoda pair, so you have the knowledge of simple component also. So Shoda pairs do exist. This is the first preliminary thing we would like to check, because as was mentioned earlier, that if this happens, then this happens. What about if, right? So existence thing. So one Shoda pair I've already told you, group itself, like G comma G, group paired with itself. That's always a Shoda pair. Fine. So just begin with some small groups, C2 cross C2. You can just play with the lattice of subgroups. Because we are looking for possible candidates of Shoda pairs or strong Shoda pairs or extremely strong Shoda pairs, what you do is just have the first group to be bigger than the smaller one, bigger than the second one. Okay, so that's what I've done in my first list. There is no other choice. And then if I want to check the conditions, what were the conditions? I'll just write here. This is cyclic. You want K to be normal in H and this to be normal in G and this to be maximal abelian subgroup of All right, these are the two conditions that you want to check. Now this is normal in G. This is the extra condition that we are putting for extremely strong Shoda pair. Yes, the definition initially wanted normalizer here, okay? All right. So if you take it on these groups, because we are in an abelian group, every group is normal. So this is just G. And for this to be, this is cyclic, is something which is necessary. So that rules out the last option. Okay, that cannot be a strong Shoda pair that we are looking for. Okay, I'll restrict myself to extremely strong Shoda pair. When I talk about other pairs, I'll mention it. All right, we are just focusing on the pairs which satisfy these two conditions. Because we are working in abelian group for this example, right? So K is, the normalizer has to be G. Okay, so we want this quotient to be cyclic. So the last case is ruled out. And what else do you want? That it should be maximal abelian subgroup of this. So when is it possible? If it is already cyclic, that's needed. That means if this is cyclic, the conditions are satisfied. Can you follow this? So are all these pairs satisfying the required conditions? So this gives you complete set of extremely strong Shoda pairs of G, right? When G is taken to be Klein's 4 group. Similarly, you can repeat the process for cyclic group of order 4, just taking small groups to see if this is doable. But abelian groups are always like easy. So maybe some non-abelian groups to start with. Are not listed for S3. Okay, maybe that's missing here. Just a second. Okay, so we'll first see what are the observations we have by now. G comma G is always extremely strong Shoda pair, and you cannot have H comma H as extremely strong Shoda pair if H is not G. Why? Can you see the reason? Because the quotient will be trivial, right? It cannot be maximal abelian subgroup of a non-trivial group, okay? So that's not the case. And if H is G, if the first part you're taking as G, then that happens to be extremely strong Shoda pair if and only if G mod K is cyclic, okay? Is it okay to follow this? And if G is abelian, all extremely strong Shoda pairs are going to be of this form, G comma N, such that G mod N is cyclic. Okay? And if you apply the theorem that we had for the simple component, if you apply it to this pair, right, and you run it over all the normal subgroups, what do you get? Walker theorem, right? You get Wdderburn decomposition, but there is something which I'm missing right now. It's not needed for abelian groups. We'll come to that in a while. But by this process, you do get Wdderburn decomposition when you are working with an abelian group. Okay, so abelian is all settled. Okay, so now I take smallest non-abelian group, symmetric group of order 3 on 3 elements, or dihedral group of order 6, and direct check, as we have proceeded earlier, will give you these 3 pairs. Okay, and if I repeat the process for D8, this is the list that I'm getting. Is everything all right? Do you see a problem? How many components do you expect for S3? You must have seen Wdderburn decomposition of QS3. How many components do you expect? 3. You have 3 extremely strong Shoda pairs. Each of them is going to give you a simple component. That's fine. But when you come to D4, how many components do you really expect? There are 4 linear representations. There is one 2-degree representation. So there have to be 5 components, right, in the Wdderburn decomposition. but then you're getting more than 5. Right? Do you see a problem here? Every pair is going to give you a simple component. And this list has 9 elements, 9 pairs. So that will give you 9 components. That is not giving you Wdderburn decomposition. So that's what I'll come to. How do we need to select our pairs so that there is no redundancy? Right? So that's what I'm trying to just point out here. That not like if you just rule out from a lattice of subgroups extremely strong Shoda pairs, that does not stop your work for finding Wdderburn decomposition. Okay? All right. So what are the obvious questions at this stage? Is there some refined method to find set of extremely strong Shoda pairs? I mean, for small groups it's okay, but for big groups, checking for every pair is not simple. So is there some refined way of doing so? Each pair is going to yield a simple component. So how do you choose a subset of it so as to obtain exact Wdderburn decomposition? Okay? And are these all Shoda pairs or strong Shoda pairs? Because we have put an additional condition. We might have lost some pairs which were Shoda pairs but not extremely strong Shoda pairs, and same thing for the strong Shoda pairs. Okay? If yes, then for what groups? And if not, then how do we find the remaining ones, or what are the conditions? Right? These are the obvious questions that we have at this stage. Let's see which of these can be answered. Okay, so there is an algorithm to find a complete irredundant set of extremely strong Shoda pairs of G. By irredundant, I mean no two of them are going to give you the same simple component. Okay? So if two pairs are giving you, I should not be saying simple component, they are not going to give you the same idempotent. For two different idempotents, you can have simple component which is same, right? You can have copies of Q, you can have copies of other things. So we will call two pairs equivalent if they give you same primitive central idempotent. Okay? So we do have an algorithm which tells us how to find a set of extremely strong Shoda pairs such that no two of them give you same primitive central idempotents, and they cover all. Okay, so what does this algorithm do? Step 1 is to find out all normal subgroups of G. Of course, this is not a very basic thing, but this algorithm asks you to do that. Then for every normal subgroup, you choose AN. This AN will work like, so we are looking for these pairs, right? We are working for these pairs. For that, so I'm giving just a rough idea of this algorithm. For every n in the normal subgroups, this is a normal subgroup, we want to create what are all the pairs that you get corresponding to this n, right? This H, is denoted by AN in this notation of algorithm. What is needed from AN? It has to be a normal subgroup of G which contains n and satisfies this condition. Okay? Okay, this is what we want at first. The choice of AN may not be unique, but then it does not affect our result. Okay, so choose one AN which satisfies this condition. And then with sorry for the interruption. And for that fixed AN, we work with more subgroups and we put some extra conditions on the subgroups of AN. We choose the ones which are suitable for us, which make it extremely strong Shoda pair and which avoids the redundancy as well. So as such, and then whatever pairs we get for every normal subgroup, we just take union over all of these, and this gives us complete set of extremely strong Shoda pairs of G, complete irredundant set, which we were looking for. But this method seems to be quite heavy, quite expensive in terms of franc maybe. So this is the reason for this is because this is meant for any arbitrary finite group. When you really want to apply it for a particular group, looking at the structure of group and with certain reductions, this gives you answer readily at times. Okay, so what are the reductions that you can possibly make? I'll list few of them. So one thing you have already seen for the case of abelian groups, what you're going to get is just these pairs. Going by this process also, you are going to get, because the conditions and the property of abelian groups, that is going to cut it down to this. Okay, and I'll list few more reductions. So, and in fact, even if G is not an abelian group, but then you're working with a normal subgroup for which the quotient is abelian, then also you just need to check if G mod n is cyclic or not. Okay, so whether you're getting a pair from that normal subgroup or not. Okay, so that's the first reduction. If it is non-abelian, if G mod n is not abelian for some normal subgroup, then we go to step 2. We find an and see if an mod n is cyclic. Even that makes our work easier, because in that case, if the second condition is satisfied, then we are done. Otherwise, that will not give us any pair. Okay? And if the center of G mod n is not cyclic, that's something not coming from just from the algorithm, but from basic representation theory, then in that case also you're not going to get any pair from that. Right? What I'm trying to say is all the conditions put are just from the group structure of G. There's no representation theory. I mean, at the back it is there, of course, but for the calculation you just are working with the group itself. Okay, so if center of G mod n is not cyclic, you're not getting any pair from that, and you can rule out such normal subgroups. And suppose if you keep getting the pairs, right? You find out some pair and you find out simple component corresponding to that. You know how it is by the theorem that we mentioned earlier. You can compute the dimension of the simple component that you're getting, right? That comes itself from the matrix algebra that is given to you. And if you keep adding those dimensions, what it should give you? You have this Wdderburn decomposition. Right? So if we just count the q dimensions, they should match. So if the simple components that you're getting and you keep adding the q dimensions, the moment they reach order of G, you can stop. Okay, you're not going to get any more. So that's what I'm writing down in the next part, that if there is a subset of, if there are some normal subgroups which give you this thing, then you can stop at that moment. All right. So all these ideas have been used to, okay, I'll come to that part also a little later in the lecture. We come back to one more question which was pointed in previous section. So first question was, how do we find extremely strong Shoda pairs? And the second was, how do we know if they are enough, right? How do we know that we are not going to get any more strong Shoda pairs, or how do we know that it gives you the complete Wdderburn decomposition and not just the few simple components? Okay, so this is theorem which says, I'll just quickly recall the definition of normally monomial group. Monomial group means you have, so a character of G is said to be monomial if it is induced from a linear character of a subgroup. Okay, and we call this character to be normally monomial if this is normal in G. That's it. Okay, so this has been proved that if G is a normally monomial group, then the idempotents that you get corresponding to these extremely strong Shoda pairs, that is a complete set, and in fact the converse also holds true. I'll just read out the result. What is it? If G is normally a monomial group, then this is a complete irredundant set of Shoda pairs as well as strong Shoda pairs. You're not going to get any more. Okay? So that leads to another question. Which groups are normally monomial? Okay, that is next obvious question. We'll come to that as well. And then E, so epsilon, remember I told you this is the candidate for H. So the pairs, the idempotents will look somewhat like this, where this pair is in the set SG that we have computed from the algorithm. So this forms a complete set, a complete irredundant set of primitive central, a complete set of primitive central idempotents of QG, right? G is the other group that you will get. So this is the pair that you are getting in that SG, the set that you have. All right. And then you can also check a group is normally monomial or not by computing these pairs itself. You have found a complete set. You can find the simple components. You can compare, you can find out their dimensions as Q algebras. If that happens to be equal to order of G, then you cannot find any more, right? But the nice thing about this is that it is group theoretic. The definition of a normally monomial group is by characters of G, that they should be of certain form, right? This is a group theoretic check that we have. All right, so just putting together all these things, what do we have? The concept of monomial groups, strongly monomial groups, normally monomial groups, Shoda pairs and everything, okay? I'll just put it together here. All right. So we have seen that they correspond to monomial groups. This is again one of the result that was quoted in the lectures, that every representation of a monomial group, in fact that follows from the criteria itself. So the irreducible characters here correspond to the Shoda pairs, right? The definition of this we have just now discussed. So character is induced from a linear character of a subgroup. For extremely strong Shoda pairs, we have that they correspond to normally monomial groups. All right. And strongly monomial groups are defined using strong Shoda pairs itself. Okay. If every primitive central idempotent is of the form e.g. hk, when hk is a strong Shoda pair, then you call it strongly monomial. So by the definitions, we do have these implications. All right. This implies this. This implies this. Okay. So this is the correspondence that we have by now. Okay. So we have, maybe I can just come back to these commands in a while, because we have these implications. These I'm putting as some exercises, but then it makes sense to discuss these questions. Some of them are trivial, some of them are not, right? Finding examples in the other direction is non-trivial, but I will not point out here. I will not point out here which ones are trivial, so that you can just try and understand yourself. Okay, so, okay, and some examples first. Normally monomial groups. Which groups are normally monomial? One thing is to check by this, but then there is a class of groups that we know is contained here, which are metabillion groups. At least every metabillion group is normally monomial. Okay. Then there's a class of groups which has been told to you, the strongly monomial. Can you tell me? No? We have seen this in previous lectures that abelian bi-supersolvable groups, they are strongly monomial. Of course, we are imposing more condition here, so we are losing out on the class of groups that satisfy this thing. And monomial groups is a huge class, you know already. So, can you find a strongly monomial group which is not abelian bi-supersolvable, which is outside the class of this? And this way, okay? Can you find out groups which are strongly monomial but not normally monomial? And this way, right? You can use gap to write down certain functions and go over the library of small groups present there. And otherwise also, if you want to construct such groups, that will be a nice exercise, right? So that because it had to be overlap of group algebra lecture and gap lecture, so these are the exercises that you can do in whatever way you want to. And there was another exercise which could not be taken up yesterday, which was to write down for some small groups, for some groups of small order, to write down complete set of primitive central idempotents of QG. Now you have a way using Shoda pairs. So at least for the small groups that we have taken earlier, you can just see by the Shoda pairs what are the PCIs that you get. Explicitly as elements of QG, you can write them down. Okay, this EGN, which does not really look very nice, if you work them out for those examples, you can really write it as group ring element. Okay, but then you need to kind of see this to understand this. Okay, and so these are the exercises related to that. Then I want to come to which some functions which are there in Wedderga and which could be relevant for this. Before that, I will also point out towards the algorithm. So as I told you that extremely strong Shoda pairs, they do not always suffice for the complete set of strong Shoda pairs. Okay? But then if we are able to do that, we are at least reaching up to strongly monomial groups. Okay? So what we can do is find out all extremely strong Shoda pairs first. Then you can find out the idempotent corresponding to that, right? And working with remaining choices of groups using certain reductions, you can see which are the pairs which are not in the list but give you the idempotent which was not in the list that you have obtained, right? I'm just repeating myself. You have one set. If that does not suffice, you look for more pairs of subgroups with a lesser choice because some of them are really ruled out, and then see the idempotents that you get from them. If they are orthogonal to the previous ones, if they do not occur in the list that you have got, then that is a pair. Okay, but then if you try working it out for certain groups, you will realize that it does most of the work for you without actually calculating idempotents, right? So if it is a normally monomial group, you can reach to Wdderburn decomposition by leaving that intermediate step of finding out the idempotent also. Okay? So here I have listed certain functions which are available in Wedderga. So is Shoda pair? You have a pair of group, you want to check is it a Shoda pair? You can check it, right? So the first, it is on 3 elements. The command is on, the input is on 3 parameters. The first one is the group, the parent group, and this is the pair that you want to check. Okay? Then there's another one parallel to this is strong Shoda pair. The name suggests what it does, and similarly for extremely strong Shoda pair. So given a pair, you can always check it with gap, whether it is satisfying this condition or not. Then we have ways to check if the given group is monomial or not. That, if I'm not wrong, that does not come via this process of finding Shoda pairs and everything. Okay. Okay, another small question here. How do we know, this we wanted to take up for tutorial, but I think it's relevant now. How do we know what theory is associated behind a function? Like if you want to check for finding out for a given group G, for this command, is gap going through all the Shoda pairs, or is it using some other method to check it? How do you know it? So there is a documentation of all the functions. I'm not talking about the documentation that you have seen as a manual. There is another documentation. When you compile gap in your computer, there's a directory there where you can see explicitly the complete algorithm. Each and every command can be seen so that you can understand what is the process going behind certain function or certain, certain command. Okay? So that generally sits inside, if you have this package file, PKG directory is there in your computer where you have installed gap, and then there are certain packages. For every package, there is this folder called lib. In that, you can see all those functions sitting there. Okay? All right. Okay. Is strongly monomial. As I said, by definition, it is a group whose definition is dependent on strong Shoda pairs. So this essentially calculates all strong Shoda pairs and gives you this. Is normally monomial group G. This does not go via character definition. This goes via the process that I mentioned just now, the equality in terms of subgroups of G, right? So that checks via this whether a group is normally monomial or not. Then you can find out complete list of strong Shoda pairs, and that will produce a set of inequivalent strong Shoda pairs. Okay, this by default you're not going to get 2 pairs in that list which give you, so irredundancy has been taken care of in the list that you get out of this. All right, so small remark, if you input the command Shoda pairs, you're not going to, this is not a valid command there. So the command here is Shoda pairs and idempotents. Somehow it calculates both the things together. And then you can just read first part of it to get Shoda pairs. Okay, so that's not a big hurdle. Okay, then if you have a list of idempotents, idempotents need not be constructed via this algorithm only. You can have some idempotents and you want to check whether they form a complete set or not. That is doable here. And this R is mentioned because these are not specific to QG. In fact, the other functions also, they are meant for semisimple group algebras. You can have finite group algebras as well. but then this particularly is okay for any unital ring R. Then you can find out primitive central idempotents by strong Shoda pairs. Why is this by strong Shoda pairs? Because you can also find primitive central idempotents using the character table, right? There is, we have a, like it was mentioned in yesterday's tutorial, we do have a good list of character tables. So via that also primitive central idempotents are computable, but then if you want to do them by process of this, then you can do this. That reminds me, we can also talk about this command if you want to compare which method is faster. So there's a command called runtime with which you can check the time taken to execute some command, right? So this is how you can compare if you're getting same output by two methods. If you want to see which one is better in terms of time, this is the command that you can use. All right. Then primitive central idempotents by extremely strong Shoda pairs, that's indeed there. And given a pair, if you have, suppose, if you have checked that it is indeed a strong Shoda pair, which is doable by gap, if you want to find out what is the corresponding idempotent, right? This was not very nice structure, right? The computer can do it for you. I mean, apparently it's not nice. Maybe if you calculate, the things are not that bad. So this was sum of these EHKs and their conjugates. This sum was taken. So firstly, you need to compute this, and then going by conjugates in the transversal, and then you get this element. There's a command for this in Wdderburn.